Pull! Oh! Yeah!
Lesson 1. Probability. What is probability and how to assign it? Begin the session with a discussion on your uncertainty over summaries generated from data, especially when data are random samples of a larger population of units. An example: people, farms, firms, and others. Example: approval ratings or proportion of people voting for a candidate. Average family income.
In the Philippines Statistical Authority's Kenya Family Income and Expenditure Survey.
Average prices of commodities.
From sample outlets.
People can quantify uncertainty through the notion of probability or chance. Suggest to learners that if they were asked for the probability that they would pass the next quiz, they may give a number between 0% and 100%. Typically, the chances of a future outcome may be based on some past experience of data collected. Very studious learners, for instance, had passed their quizzes 100% of the time, while average students had passed their quizzes 85% of the time. When considering probabilities of events, learners should be guided to consider a particular context wherein possible outcomes are well defined and can be specified, at least in principle, beforehand. This context is called random process, wherein we do not know which of the possible outcomes will occur, but we do know what is on the list of possible outcomes. Learners can be informed that it can be also helpful to view the probability of an event as its long-run empirical frequency, or the fraction of times the event may have occurred under repeated trials of the random process. In the next lesson, we shall call this the empirical probability and mention that in practice, we expect these empirical probabilities to stabilize towards some theoretical probability. This is called the law of large numbers. Think of random processes and an event where the outcome is certain. Examples may be getting ahead in the next toss of a two-headed coin or getting a number of at most 6 when a die is thrown once. The outcome is impossible. Examples may be getting a tail in the next toss of a two-headed coin or getting a number greater than 6 when a die is thrown once. The outcome has an even chance of occurring. Examples may be a couple having a boy as their next child or getting a red card when randomly selecting a card from a deck of cards. The outcome has a strong but not a certain chance of occurring. Example 8, be getting a sum of at most 11 when a pair of dice is thrown. Then, ask them the probability associated with these events. Answers: 100% for certain events, 0% for impossible events, and 50% for outcomes with even chance for occurring. For the example in D, there are 36 possible outcomes for tossing a pair of fair dice. 35 of them will have at most a sum of 11, so the chance of getting at most 11 is 35 and 36. The closer the value of the probability to 1, the most likely the event will occur. The closer it is to 0, the less likely it will occur. The following properties of the probability of an event. The probability of an event is on a negative value. In fact, it ranges from 0
When the event is impossible.
to 1.
When the event is sure.
The closer the value to 1, the more likely the event will occur. The probability of the sure events is 1.
In other words, the chance of a sure event is 100%.
If A and B are mutually exclusive events, meaning it is impossible for these two events to occur at the same time, then P open parenthesis A or B closing parenthesis equals P open parenthesis A closing parenthesis plus P open parenthesis B closing parenthesis. This is called the additional rule. A more general result, also called the general addition rule, states that P open parenthesis A or B closing parenthesis equals P open parenthesis A closing parenthesis plus P open parenthesis B closing parenthesis minus P open parenthesis A and B closing parenthesis. Geometrically, from a Venn diagram, the area of the union of A and B is the sum of the areas, but if we added the intersection of A and B twice, so we have need to subtract this area from the sum of the areas of A and B. Illustrate to learners that these properties can help us more readily compute for the probabilities of events. P, at most a sum of 12 when tossing a pair of fair dice, equals P, at most a sum of 11 or a sum of 12 equals P, at most a sum of 11 plus P, sum of 12. But P, at most a sum of 12 equals 1 and P, sum of 12 equals 1 and 36. Thus, when looking for the value of P, at most a sum of 11, P, at most a sum of 11 equals 1 minus 1 and 36 equals 35 and 36. In general, if we are interested in AC, the complement of an event A, an example, the event that happens when A does not. Since P open parenthesis A or AC closing parenthesis equals P open parenthesis A closing parenthesis plus P open parenthesis AC closing parenthesis and P open parenthesis A or AC closing parenthesis equals P open parenthesis sure event closing parenthesis equals 100%. Thus, P open parenthesis A closing parenthesis plus P open parenthesis AC closing parenthesis equals 1 or equivalently, P open parenthesis AC closing parenthesis equals 1 minus P open parenthesis A closing parenthesis. In consequence, the chance that an event does not occur is 1 minus the chance it does occur. In terms of a Venn diagram below, given a sure events S represented by a square with area 100% and an event A represented by the triangle whose area represents the probability of A, then the chance of an event A not happening is 1 minus the chance of event A happening. An example, area of the square minus the area of the triangle. Extra notes. Historically, probability was studied by gamblers who wanted to increase their winnings, or at least decrease their losses. Probability describes random behavior, but does anything really happen at random? Even Albert Einstein, when confronted by theories of quantum mechanics, was said to have pointed out that God does not play dice. Yet, many events, especially in nature, seem to display random behavior. In many real-life situations, we will be able to model this by random processes and thus apply probability to understand the behavior of these situations. Main lesson: computing probabilities of events. The calculation of the probability of an event may sometimes be considered directly from the nature of the phenomenon or random process with some assumptions of symmetry. Some underlying outcomes may be equally likely by assumptions such as fair coins and fair dice. In practice, these assumptions need to be tested and will be the subject of inquiry in future lessons. These assumptions are simplifications to help us calculate probabilities. Example 1. A box contains green and blue chips. A chip is then drawn from the box. If it is green, you win 100 peso. If it is blue, you win nothing. Learners have a choice between two boxes. Box A with 3 blue chips and 2 green chips. Box B with 30 blue chips and 20 green chips. Which would learners prefer? Some learners may say B, but tell learners that it actually should not matter because the chance of winning 100 pesos is 2 and 5 minus 40% in box A, while in box B, the chance of winning is 20 and 50 minus 40%. Same probability.
Conditional probability. Sometimes we may have extra information that can change the probability of an event. Give the following definition of conditional probability. The conditional probability of event A given that B has occurred is denoted as P open parenthesis over B close parenthesis and defined as P open parenthesis A B equals P open parenthesis A and B close parenthesis over P open parenthesis B close parenthesis. Example number 2, suppose that we want to randomly select a student from among grade 9 to 12 in a certain school. Grade 9, male 84, female 145, total 229. Grade 10, male 40, female 82, total 122. Grade 11, male 36, female 52, total 88. Grade 12, male 25, female 36, total 61. Total of female is 185. Total of female 315. Total is 500. The chance of selecting a grade 11 student given that the student is a male can be computed as follows. Define events A and B as A equals event the student selected is a grade 11 student. B equals event the student selected is a male, then P open parenthesis and B close parenthesis equals P A and B equals 84 over 500. P open parenthesis B close parenthesis equals 185 over 500 equals 84 over 185. Example number 3. A king comes from a family of 2 children. What is the chance that the king has a sister? As a king comes from a family of 2 children, we are given extra information that this family of 2 children has a boy, the king. What we want to compute here is the probability that the sibling of the king is a girl. Let be the event of having at least one boy. So, B equals bracket open parenthesis B and B close parenthesis open parenthesis B and G close parenthesis open parenthesis G and B close parenthesis bracket where open parenthesis X and Y close parenthesis means the 6 of each child, and the possible values are B for boy and G for girl. Then A is the event that the king's siblings is a girl. A equals bracket open parenthesis B and G close parenthesis open parenthesis G and B close parenthesis bracket. While the original sample space S of all possible outcomes is S equals bracket open parenthesis B and B, close parenthesis, open parenthesis G and B, close parenthesis, open parenthesis B and G, close parenthesis, open parenthesis G and G, close parenthesis bracket. Each outcome has 1/4 chance of occurring. However, P open parenthesis and B, close parenthesis equals PA and B over P and B equals 2/4 over 3/4 equals 2/3. Independent events. Sometimes, the extra information provided may not really change the probability of an event. In this case, the events are said to be independent. The conditional probability of A given B may still be equal to the unconditional probability of event A. Two events A and B are said to be independent if P open parenthesis A and B, close parenthesis equals P A, close parenthesis P, open parenthesis B, close parenthesis. This is also called as the multiplication rule. Intuitively, we call events such as tossing a coin or dice several times independent since future tosses are not affected by previous outcome. Example number 4. The possible sum of two tickets drawn in a replacement are shown in contingency table and tree diagram below. First ticket. In consequence, the probability of getting a sum of 3 is P sum of 3 equals 2/9. While if the tickets were drawn without replacement, we have second ticket. P sum of 3 equals 2/6 equals 1/3. Exercise number 5. Identify how many of them have a birthday in January. Try to see if you can get a match. Go to February if you don't find anyone that match. Then March, and so forth. The chance of two people having different birthday is 1-1/365 equals 364/365 equals 0.997260. The chance of n people having different birthday is 1-1/365, 1-2/365, 1-n-1 equals 365. So the chance that at least two of them will have the same birthday is Pn equals 1-1 equals 365, 1-2 equals 365, 1-n1 over 365. We have the probabilities computed below for several values of n. Pn 10, 11.7%, 20, 41.1%, 23, 50.7%, 30, 70.6%, 50, 97.0%, 57, 99.0%.